Many real-world mathematical functions carry high computational costs. To maintain efficiency, we replace these complex curves with simpler polynomials that mirror their shape. In fields like aerodynamics or real-time graphics, we need these mathematical approximations to function as reliable substitutes, calculating results instantly without taxing the processor. This replacement happens within domain CAB, a closed interval from A to B. We judge quality using the Supremum norm, measuring the widest gap between target and approximation. Unlike pointwise methods, uniform approximation strictly traps error inside a tolerance band, preventing localized spikes. This approach establishes a guaranteed error ceiling. It ensures the approximation's deviation never exceeds a safe limit at any point along the interval. When we analyze the error function, we look for extremal points. These are the specific locations where the gap between the functions reaches its absolute maximum value. If the error function has too few of these points, the approximation can be tweaked. We can effectively push the error down to find an even closer fit. To ensure there is only one best answer, we look for the Haar condition. This requires that the functions in our approximating subspace have a limited number of roots. The Haar uniqueness theorem states that a best uniform approximation is only unique if the subspace we choose satisfies the specific algebraic condition. Consider standard polynomials. Do they possess the algebraic properties required to meet this rigid test? Polynomials of degree n satisfy the Haar condition because they can have at most n roots. Mathematically, this ensures the Vandermonde determinant of the system cannot equal 0, guaranteeing a unique solution. The Haar condition proves that polynomials are not just convenient, they are a mathematically rigid standard for creating reliable, unique approximations. The equioscillation theorem tells us how to recognize a perfect fit. If the error alternates signs, hitting its maximum exactly n+1 times, it is the absolute best approximation. Chebyshev polynomials are designed to produce this behavior, distributing error by oscillating relentlessly between positive and -1. To see this in practice, let's try to approximate t to the n using a polynomial of one lower degree. We want to find the smallest possible maximum error. We can rearrange the Chebyshev polynomial to isolate the t to the n term. By subtracting a scaled version of the Chebyshev polynomial, we are left with a lower degree polynomial, y of t. The resulting error is exactly 1 over 2 to the n minus 1. Because this error term is a scaled Chebyshev polynomial, it alternates perfectly, proving we have found the unique best approximation. This illustrates the difference between Taylor and Chebyshev. Taylor polynomials are precise at a single point, but fail at the edges. The Chebyshev approach ripples the error evenly across the entire interval. This is the logic of the minimax solution, sacrificing perfect accuracy in one spot to minimize the maximum error everywhere else. It is the invisible system that ensures our digital calculations remain stable and precise.